Hello and welcome back to another lecture from Organic Chemistry. In this lecture, we're going to go through a hydroboration-oxidation reaction. And in hydroboration-oxidation, we will have an alkyne and molecule that we're going to treat it with BH3 or the version of BH3 in the presence of solvent of THF and two reagents. One is going to be hydrogen peroxide and the second one will be sodium hydroxide. And from alcohol or alkene, we learned that this one is supposed to give us an alcohol, but because we will have alcohol attached to a double bond, it can go through a keto-enol tautomerization, and it will give us an aldehyde or ketone. It depends what we start with. As you see here, and we are using BH3 to run the reaction, but in reality, BH3 is not that favorite, starting compound to use it for alkyne because it has a 3 hydride, and so that means it can actually add more than 1 hydrogen to the triple bond. And in order to minimize, like number of the side product and also increase the efficiency, we try to limit it by using compound like this, BH1, and then we replace 2 of the hydrogen by alkyl groups. And so the purpose is to minimize number of side product and also increase the efficiency. This system is going to go through anti-Markov-Nikov addition. What does it mean? It means if you remember from alkene chapter, we said whenever we treat it with BH3 in the presence of H2O2/OH, we're supposed to get an alcohol, but the alcohol, it will show up on a carbon with less substituent. This carbon is a tertiary, while that one is a primary. Alcohol shows on the primary carbon, and that's the reason we say this addition is going through anti-Markov-Nikov rules. And because we do have OH inside the solution, whenever we get the enol, it will go through tautomerization, and by this time it will go through a basic version of it. And as you see here, and OH, it will attack the base, it will attack hydrogen from the alcohol group, and now that's going to leave us with oxygen that it has a 3 lone pair. It can share one of the lone pair with carbon. That's going to give us a double bond, but then we get a negative charge on carbon. And now what will happen with carbon? That carbon very soon it will take H from water in order to give us aldehyde or ketone. Okay, let's practice an example. We have a terminal alkyne, clearly is non-symmetrical, and because it has one H attached to one side of the triple bond, and other side we have a phenyl ring. And the addition is going to happen in a way that the hydride will be closer to the carbon with more substituent, and boron, and it will be closer to the carbon with less substituent. And remember, boron has an empty orbital, so it's capable of accepting electron from carbon. This is hydride, not hydrogen atom, or like or hydrogen or hydrogen ion. Like when I say ion, I'm talking about positive charge. A proton is not a proton, and because it has a negative charge, so that means it's going to donate electrons to the carbon. And very soon we will get one sigma bond between carbon and hydrogen, and the triple bond it will get reduced to a double bond. And now what will happen with the negative charge? Negative charge, technically, it will be given to boron. And now, I know I have like the hydrogen peroxide inside the system, and that hydrogen peroxide, because it's acidic, very soon it will react with hydroxide, and it will give us this species. And this species, through multi-steps, it will replace the Br2 by OH. So I'm going to say, we do have hydrogen here. Now we're going to replace the Br2 by OH. That's an enol. Okay, it's a double bond. So I say En, and also because I have OH, I'm going to say this is an alcohol. So I call it enol. The enol, it can go through tautomerization. I have a base. And this base, it can go after the acidic hydrogen. It will take that one out of the system, and it will give us water. And now oxygen with a negative charge, and we do have hydrogen here. Now, very soon, this lone pair will be shared with carbon in order to make a double bond. And so what will happen to this double bond? This double bond, it will be moved to carbon, and we will erase this double bond. We will have a lone pair on this carbon, and we had hydrogen there. Now we have a double bond between carbon and oxygen. That's aldehyde until now. But we have a negative charge, and this one very soon is going to find water, and it will take hydrogen from water, and that's going to give us H here. We had one H there, and double bond with carbon, and that's an aldehyde. So if you run if you run hydroboration-oxidation reaction with a terminal alkyne, you will get an aldehyde. always is going to give you aldehyde. The reason for it, because it will favor a carbon with less substituent. And this one is this carbon is a primary, so it will put the carbonyl group on the primary carbon and versus the secondary. Okay. So from now, we know anytime we start with terminal alkyne, we will get an aldehyde. Now, what will happen if I change position of the triple bond? It depends what you start with. You might get different product. Now, if it's a terminal, regardless of whether it's aliphatic or aromatic, you will get aldehyde. So in both cases, we got aldehyde first and second one, and here we have a phenyl ring attached to the triple bond. Still, we got an aldehyde. But if you turn if you move the triple bond and make it internal instead of terminal, so for those two, so we had terminal and the alkyne or triple bond. Now we have internal. And in internal, it depends whether the molecule is symmetrical or not. You might get one ketone or mixture of them, maybe two ketones. Okay, and I'm going to review these two next slide. Okay, now let's go back and compare all the methods that we used until now. So one method was like, let's use an acid catalyzed reaction. Okay, and acid catalyzed hydration in the presence of mercury, that's going to give us a ketone if we start with terminal alkyne. Terminal alkyne. Now, if it's a terminal, clearly it's not symmetrical because one side you have H. Now, if you start with acid catalyzed, it will follow Markov-Nikov rules and it will give you a ketone. Okay, always ketone. Why? Because it will favor the carbon with more substituent. And that's not going to be a terminal carbon. It will be inner carbon. And because it's an inner carbon, that means we will have substituent here and is anything other than hydrogen. And because that's not a hydrogen, it's a methyl, we will get a ketone. Now, if we go with boron, boron compound, in that case, the reaction, it will favor the terminal carbon. And because it's going to put the functional group on the terminal carbon, we will get an aldehyde. Okay, so I'm going to highlight what happened until now. With boron, it will go through anti-Markov-Nikov rules, and it will give us aldehyde. Now, what will happen if we make it internal alkyne? Now, if you go with acid catalyzed reaction, in that case, you will get mixture. Mixture, but both of them are ketones. Okay, both of them are ketones. Now, how about boron compounds? Again, we get mixture, and both are ketones. Now, like which one is the major product, that's a different story. It depends, what you start with. If you, for example, if you play with the steric effect on R groups, you might favor one of the product, but that's not subject of today's lecture. Okay, in both cases you will get ketone. And so say this: no aldehyde. We're not going to get any aldehyde. Now, what will happen if it's asymmetrical? Still no aldehyde, but we will get only one ketone. Okay, only one ketone, and that's an important point that you need really like to remember it whenever you face with such a question. Terminal alkyne will give you might give you aldehyde if you start with boron compounds. Now, terminal, it can give you a ketone, so both ketone and aldehyde are possible for it. But when you are using internal alkyne, only and only you get ketone and no aldehyde at all. Okay, last method that I'm going to practice, it will be the Friedel-Crafts and the acylation. And then we have a benzene ring that we treated with a Lewis acid and one compound that it has a chloride attached to a carbonyl, or this acyl technically groups. And the aluminum chloride is a Lewis acid. That means it has an empty orbital. Very soon it will go after the chloride. It will take the chloride out of the system. And so it will be taken out of this in a system. It will leave us carbon that's attached to oxygen with a positive charge. But carbon, it can be stabilized because oxygen, the neighbor, has two lone pair and it can share one of the lone pair with carbon. And if this one happened, carbon will be carbon will be acted or completely saturated. But the problem is, when I say saturated, I'm talking about 8 electrons. Carbon will have 8 electrons, But the problem is that we will have a positive charge on oxygen, and oxygen does not like a positive charge. So it's not that stable, but stable enough until it will find the benzene ring. Why benzene ring? Because the benzene ring, it has six pi electrons, and those pi electrons can be shared with carbon. And at the end, we will have interaction between these two. And so now we need to remove that hydrogen. Why? Because if we remove hydrogen, we can restabilize, reestablish the, the aromaticity, and the system will be stable. Okay. Now, you heard about the Friedel-Crafts many times, and then the Friedel-Crafts, it depends what you start with. You might get different product. Now, if you start with an alkyl halide, and just simply it will, it will take aluminum, it will interact with a chloride, and we know chloride attached to carbon, so that means we're going to have a positive charge here, and this one will get the negative charge. And remember, we do have 3 more chloride attached to aluminum, and now this one, it can actually interact with the ring, with the benzyl ring, and it will just simply replace one of the hydrogen by here. We will replace one of the hydrogen by methyl group. What will happen to the hydrogen? Hydrogen, it will be paired with the chloride. It will give us HCl. And in case of, acetyl chloride, and this one, it will give us such a compound. Again, aluminum, it will interact with the chloride, and chloride is attached to the carbonyl. And chloride completely can be taken, and it will be taken by by the aluminum. And so in that case, we'll have aluminum chloride, and that's going to leave us with this species, the one I'm going to highlight. Forgive me. And that's going to give us a carbonyl that's attached to benzyl ring. And now what will happen to the chloride? The chloride, again, it will react with hydrogen, and it will give us hydrochloric acid. Of course, in both cases, we will regain the aluminum chloride or the Lewis acid. So that one at the end, we will get it. Okay. Now the difference between them, the top one, you just simply added the alkyl group to the benzyl ring. In this case, you added the carbonyl to the ring. Now that carbonyl group, I can actually run it, like get involved with some reaction. I can reduce it, or maybe add, for example, or turn it to, let's say, an alcohol or something else. And this is going to be the end of this lecture. And thank you very much.